Welcome to the 50th episode of NASA Science Live. We are so thankful you could join us for this special milestone and take part in another opportunity for you to interact with NASA experts and have your questions answered in real time. I'm your host, Megan Cruz, and today I am so excited to chat with you about Sunday's historic event, NASA's OSIRIS-REx, the first U.S. mission to deliver a pristine sample from an asteroid to Earth. Now, if you have questions throughout today's show, you can send them in using the hashtag AskNASA on social media, or you can drop them into the comment box wherever you're watching. Joining me now are two experts to discuss this incredible mission and explain what's next for the asteroid sample. We have Dr. Dante Loretta. He is OSIRIS-REx's principal investigator from the University of Arizona. And then we also have Dr. Scott Sanford, science lead for the OSIRIS-REx sample return capsule from NASA Ames. Thank you both for being here.
Thank you.
All right, so on Sunday, let's recap for everyone. On Sunday at 10:52 a.m. Eastern Time, the OSIRIS-REx capsule you see right there landed in the Utah desert carrying a sample of Bennu, a carbon-rich near-Earth asteroid. You know, I was watching this live broadcast from home. It was so exciting to see that capsule streak across the sky. Then the main parachute opens, bringing it down for that soft landing again that you see right there. Some of the team observing the capsule soon after it came down. Dante and Scott, you know, I know both of you were there for the landing. Describe how you must have felt to be on the ground for that historic moment. I know it must have been really emotional.
Yeah, thanks, Megan. It was the culmination of a 20-year journey for me personally and for this team. And emotions were riding high. You know, as we say, the spacecraft's not just fueled with hydrazine. Our emotions are carrying it through space to that journey to Bennu and back to the Earth. You know, it was full of heart-pounding moments, but when we heard that that main chute had deployed and the capsule was coming down for that gentle landing, I literally broke into tears. I was sitting right next to Scott in helicopter 4 on our way out, and I just couldn't hold back. It was just all of the stress and all of the tension just flew out of my body, and I was filled with pride and relief, quite honestly, that we had made it down to the surface of the Earth.
Yes, Scott, do you have anything to add?
You know, it's going to take me a little while to unpack it all. And the problem is we keep doing things, so I can't catch up. But certainly there was a sense of relief. I let Dante do the cheers for me, but I had some of the same sentiments. Also, first seeing the SRC, they're sort of filled with awe to just think about all the places it's been and the things it did. It's just amazing. And just anticipation too, because once the capsule came down, we had Bennu. The day before, we didn't have Bennu. So now there's a whole bunch of things we can do that we couldn't have done before. And so it's just really exciting.
And speaking of exciting, since then, Lockheed Martin, who built the sample return capsule, as well as the spacecraft, has opened that capsule, and we're getting a first look inside. There it is, a picture taken just hours ago. Dante, walk us through what we're looking at right now.
Yeah, this is the scientific treasure box. So what you see is the science canister has been opened up. It's kind of like a clamshell. So the lid is behind us. The white area in the middle is a filter. I think Scott will tell us more about that because that's part of his science investigation. It's on an avionics deck or that aluminum plate. And that air filter looking device right there in the center, that's the touch and go sample acquisition mechanism, or as we call it, the TAG-SAM. That's the device that touched the surface of Bennu and where we believe inside there is our scientific treasure. So this is our first glimpse of what we might have. There's good indication that we might have sample. You can see some black dust on the deck there. We've got our work to do to figure out really what's going on with all of that material.
I can hear the excitement in your voice, and I know you were excited because we have video of you inside the room when they opened up the canister there. Can we pull up some of that video to take a look at it as well? Kind of walk us through more of the process, Dante, if you can, again, what we're looking at, and just to explain how complicated this all is.
Yeah, so what you saw from the landing was the capsule, which had a heat shield and a back shell, and then this was inside. It's kind of like one of those nested dolls. So you had the heat shield, and then you've got the science canister, and they're pulling the lid off right now. And then sitting inside a capture ring is that tag SAM device, and it's kind of clicked in like a ski into a boot into a ski. And of course, I'm thrilled here because this is the moment we've been dreaming of, right? We can see the thing that touched Bennu is now in our laboratories. And of course, we can't wait to get inside. We still got a lot of work to do. We still got to get inside that tag SAM. That's where the real treasure is. But we know how to do that, and the team is ready and raring to go.
And for those who don't know, the person cheering in that bunny suit, that was Dante. You explained to me what was happening there. You said that you were texting the picture that you took of the opening of the canister to the rest of the team, right?
Yeah, on the other side of that window that I'm looking to is an observation room. And my mission sample scientist, Harold Connolly, my mission implementation system engineer, Anjani Pollitt, members of the curation team, like Francis McCubbin, the lead astromaterials curator, they're there observing us as we're operating in the clean room. And I'm taking those pictures and then airdropping them over to them so they can get them out to the team to start to process, analyze, and think about what's going to happen next. We have a big important decision ahead of us because we do get to sample some of that dust very quickly, probably tomorrow morning, and that'll go to the science labs here at Johnson Space Center for what we call our quick look analysis. It's a basic assessment. First of all, is that actually part of Bennu, or is it something else, some other dust? Probably Bennu, but of course, as scientists, we've got to confirm, we've got to get the measurements, we've got to verify that that's indeed what we're looking at. So the team is going through those images that I took and making some really important decisions this afternoon.
Yeah, so still quite a process, and we'll go into a little bit of that more in the show. But I do just want to go to Scott right now really quick. So Scott, you're the science lead for the sample return capsule. Talk to us. I mean, did it perform as expected? I mean, it was really amazing hardware to do what it did.
Yeah, the sample return capsule, or SRC as we often call it, was required to do an awful lot of different things for us. And it really performed. I mean, it had to open and close at the right time so as to get the sample tucked away in it. It had to seal tight and keep the sample safe the whole time it was in flight back to the Earth. And then it had to be delivered at just the right place and time in the Earth's atmosphere so that it re-entered and ended up at the recovery site. And then, of course, it had to do the job of protecting the sample from the intense heat that happens when you enter the atmosphere at that high speed. You can see in these pictures the black char that's on the sample return capsule from that heat of entry. And then it had to pop open its parachute, slow itself down to its final velocity, and land. And as you can see, it was we stuck the landing. We came down right on the nose.
Yeah, other than the char that we see obviously on the capsule there, I mean, it really looks almost still perfect. No dings, no scratches, nothing like that.
Yeah, from the marks on the ground, we can tell that it hit almost straight down, but it did a little hop onto its side, and it bounced off its side and rolled back into the original hole. So if it was a gymnast, it would have been a 9.95 because it hit the landing, but it had to make a little hop.
So Scott, now that the sample return capsule is back and there's all the science that has to be done on what's inside, obviously what it brought back, the sample, your job isn't over though, right? Like you still have a lot to go with this mission.
Yeah, for the whole science team, now we get to do the analysis of the samples, which is really key. But for the SRC, we also are doing some things, making measurements and doing analyses to understand how well it performed, and also we can use information from the SRC to inform us about potential contaminants and to make sure we know how to recognize them if we find them in the Bennu sample. And so we'll get some science out of those analyses as well as engineering knowledge.
So Dante, back to you again. Let's talk about that process that you started to talk about. So canister is open, and let's take every opportunity to show that picture of the canister open again. But the canister is open, so now what? When do we get in there to look at the sample and really know what we have?
Right. So when we look at that image, you can see that the tag SAM is still locked into place. And there's an indication that there's a ring of black dust around there. And we're hopeful that that actually is asteroidal material. So what the team is doing right now is I took this image, I took a series of other images, lots of different angles, and they're going to go through and we get to pick an area where we can collect material probably first thing tomorrow morning. And I have what I call my Tiger team standing by. That's a group of scientists, both from NASA, University of Arizona, Purdue University, and they're ready to get this into the laboratories. We're also going to send some out to our colleagues at the Natural History Museum in London because they have some special expertise that we want to take advantage of. And the first question is that actually asteroidal material? Most likely it is, but we have to do that verification. And then we're going to start to test, okay, is Bennu made out of what we think it's made out of based on the remote sensing we did with the spacecraft when we were in the vicinity of the asteroid? And then the curation team's got to go through and they're going to collect all that material, containerize it, get it secured. There's some witness plates on top of Tag SAM and other places around there that recorded the environment that all of that hardware saw when it was in flight. That needs to be secured. And the real moment that we're excited about, and we may get to it this week and we may not because we're going to go as carefully as we need to, is pulling the Tag SAM off that capture ring, flipping it over onto a stand, and we'll get to see the bottom of it, the part that actually touched the surface of the asteroid. There's contact pads, which are designed to pick up fine-grained material right from the surface, and maybe we'll even get to peek inside. There's that infamous troublemaker rock that propped the flap open right after we collected the sample. I'm looking for that, just to say we got you back on Earth, but also we think it's a really nice large stone, so we're excited to see if it's there. And then we'll move Tag SAM into its own cabinet, and there's an elaborate process to disassemble it, and that might take as much as another week or so before we start to get that bigger material out. So that's the treasure box. That's what we're hoping to have some information, maybe by mid-October, that we can share with our fans and our viewers around the world.
Yeah, obviously, as you said, an elaborate process, so we'll be keeping an eye on everything, and I know that we're hoping, right, to be able to share some information with everybody on October 11th at 11 a.m. Eastern Time. Right now, we're inviting people to tune into NASA's YouTube and social media channels to see the actual sample and discover what researchers like Dante and Scott have discovered so far. So again, set your calendars, your phones. I know I have. Okay.
Yeah, we'll have something to say by then, Megan. We'll have something really interesting by October 11th. We're optimistic we'll be able to share some really great news on that by that time.
That's exciting. Okay, so the question on some people's minds might be why this particular asteroid? What do we hope to specifically learn from Bennu? If Dante, you want to start.
Yeah, Bennu's a very special kind of asteroid. It's dark, and we think that means it's loaded with a very important chemical element, carbon. Carbon is the central element to all life on Earth. And you got to remember, Bennu and the minerals that it's comprised of formed over 4.5 billion years ago at the dawn of our solar system. And it represents the kinds of objects that we think brought the water that's in our oceans, the molecules that's in our atmosphere, and maybe even the organic material that led to the origin of life on our planet. So we're going back to the distant past to try to understand and address the big question, where did we come from? And maybe if we can figure that out, we can start to say, are we alone in the universe? So we picked Bennu because of this really interesting composition, and we can't wait to get in and verify. That black dust that we saw on the deck there surrounding Tag SAM gives me some hope, because one thing carbon does is it makes things very dark and very black. So immediately we have a good sign that we might have actually brought that kind of material back from this asteroid.
And Dante, Bennu was also chosen too, right, for the study of planetary defense.
Yeah, that's actually a great part of our mission. So we had to pick an asteroid that was easy to get to after you launched off the Earth, rendezvous with, and get back. And because of that orbital dynamics, that means Bennu comes very close to the Earth, and in fact, in the future, may come uncomfortably close to the planet. It is a potentially hazardous asteroid with a small but non-negligible chance of impacting the Earth about 160 years from now. So I don't want people to worry too much about this happening soon, but this is an important insurance policy for this particular asteroid. But I think more importantly, we have developed the technologies now to get out to one of these objects, characterize its physical and chemical properties, and plot its future trajectory hundreds of years into the future. So in the event that we have to deal with any incoming asteroid, the information and the knowledge that we gain from OSIRIS-REx will be invaluable to those future activities.
Scott, how long have you been a part of this mission, and how does it feel like today after all that time?
Well, let's see, Dante's it been almost 20 years now, I guess, since the very first time we started to suggest to NASA that this would be a good thing to do. So, yeah, it seems kind of like a lifetime.
Just about.
So, yes, Dante, he alluded to it, that you've been with this project for 20 years. How do you feel?
Yeah, we first conceived of this idea in 2004, February, so almost 20 years ago now. And it is a lifetime pursuit, right? I mean, we dedicated our careers to making this mission succeed. And it was all driven by what we were about to embark on, which is sample analysis, right? So in 2004, we were like, wow, wouldn't it be great if we could have a fresh sample of carbon-rich asteroid in our laboratories to address these outstanding questions that we can't answer any other way? And persistence, patience, plenty of heart-pounding moments, including the ones that we had on Sunday. Later, here we are, mission success. We have brought this capsule to Johnson Space Center. We've opened it up, and we've just got a few stages to go before we can really declare that we have done everything that we've promised this agency we would do.
Great. And if I haven't said it, congratulations to you guys on all this so far.
Thank you.
Now we have lots of questions coming in from viewers watching online. So remember, you can submit those questions using hashtag AskNASA or posting that in the comments section wherever you're watching today. Okay. So our first question is from General Space 3 on Instagram, asking, what's the significance of having this asteroid sample? Will it help with space exploration?
That's a great question. Yes, absolutely. There's many aspects to the OSIRIS-REx science investigation. We already talked about the origins, the fact that Bennu is a treasure trove from the dawn of the solar system, and we talked about the security investigation, Bennu being a potentially hazardous asteroid, and our ability now improved to predict its future trajectory. But another part is resource identification. Bennu is an accessible object. As these things go, it's relatively low energy to rendezvous with, and now we've proven to bring material back to the Earth. One element or compound that we think is particularly abundant on this asteroid is water. And water you can process into liquid hydrogen and liquid oxygen. That's one of the most powerful rocket fuels that we know of. So I love to think about in the future, people will be taking the information we collected from OSIRIS-REx, using it to design these asteroid mining missions, and building these fuel depots in space to further exploration to the surface of the moon, to Mars, and beyond.
Really, it's enabling even more science than maybe you guys had even thought of when you first created this idea.
Absolutely.
All right, and we have another question here. Actually, many of our viewers are asking a very similar question. What happens to the OSIRIS-REx spacecraft itself? Does it burn up in the atmosphere?
Well, the good news is the answer is no, it will not burn up in the atmosphere, because right after we released that sample return capsule, we fired our rocket engines and moved away from the intercept trajectory with our planet that we were on. And the name changed. It is no longer OSIRIS-REx. It is now OSIRIS-APEX. It is on a journey to another very important near-Earth asteroid named Apophis. And I'm really proud of the legacy. Apophis is a fascinating object. It's about 300 meters across, so a little smaller than Bennu. But in 2029, it's going to come within 20,000 miles of the surface of the Earth. That's closer than our weather satellites orbit right now. So it's the biggest, closest approach of an asteroid for 1,000 years. And I'm passing the torch. The new principal investigator is now Professor Daniela Della Testina from the University of Arizona. She's taking the reins. It's her spacecraft and her team. They're going to lead this next journey to Apophis.
Scott, you might want to take this next question. So this is from Facebook. During entry, did the intense temperature of the capsule have any effect on the sample?
So, yeah, this is one of the important things the capsule does, is it kind of acts, so when we get a meteorite, it enters the atmosphere, and a large part of the meteorite is basically vaporized and is lost. So rather than us losing our sample this way, the heat shield on the SRC actually does the ablating. And so as you generate heat, it's carried away is this gas. You see this trail behind in the image here. This is the heat of deceleration going away. And so the heat, a lot of the heat doesn't penetrate into the middle of the SRC because the hot material is swept away before it can conduct any heat inside. So the analysis that's been done suggests that even though the outside in this plasma can be 5,000 degrees or so, the inside of the capsule is not expected to get above about 50 degrees C. So this heat shield protects our sample from that very severe environment and just sweeps it away.
Yeah, that's so impressive. Hackman617 on YouTube asks, what are some of the things that this asteroid sample will tell us about how our solar system formed? Will the importance of this mission be understood by future generations?
Excellent question. Absolutely. So as I mentioned before, we're looking at ancient material, older than any rock on Earth, even older than our planet itself. And we're really interested in the water, which probably formed as icy material out in the outer solar system when we were still a protoplanetary disk. When planetary systems are forming, these giant molecular clouds collapse, you form a star, and then the material that's left over creates a disk. And inside that disk, you have all this fascinating chemistry taking place. So we're looking at how did water get into the solid material? What happened when that ice got into an asteroidal-sized object? It probably got nice and hot and melted and formed a fluid and altered the minerals that were originally present. So we really want to understand protoplanetary disk and asteroid geological processes to figure out how these minerals and chemistry changes and ultimately how they get delivered to the inner solar system to make Earth a habitable world.
I really am interested in this question on Instagram. What was the biggest challenge for this project, or maybe you personally? I think either of you can answer that question as well.
Scott, you want to start?
I'm trying to think what's biggest. There were a lot of challenges, so but the team worked their way through all of them. I mean, it certainly one of the challenges was Bennu didn't get our proposal in advance. You look at some of the artist conceptions of what the tag was supposed to look like, and the pictures of the asteroid show it looking like a kind of gentle beach of sand. And we got there, and it was this gigantic jumble of boulders. And so we really had to back up and figure out where are we going to get this sample from.
Yeah, and I would say personally, right? It's we say space flight is long periods of boredom punctuated by moments of extreme terror. And so you've got to learn to keep your cool when things are really happening and the moments are arising. And the thing that has got us through all of that is teamwork, right? This is an amazing team. It's University of Arizona, Lockheed Martin, NASA, Goddard Space Flight Center, Johnson Space Flight Center, Ames Research Center, where Scott is. We all came together as one team. And that is what allowed us to overcome all the challenges and not only just perform, but to excel, right? One of the things I'm most proud of is OSIRIS-REx has just nailed every aspect of our flight program. Our launch was beautiful. The rendezvous with the asteroid, even as challenging as Bennu was, we figured it out. We went down, we got that sample. We got so much sample, it was overflowing. We got it stowed safely away, finished that 2.5-year journey back to the Earth. And of course, that beautiful pinpoint landing that we saw on Sunday. So all of those were extreme challenges. Every one of those is really hard. And we just nailed it because of the outstanding capabilities of this team.
Yeah, what you guys were able to accomplish so far is super outstanding. Having this question from, which one do I want to ask? Let's see. Lucas Weezer on X asks, why did you pick this specific asteroid? Also, this other question, how old is Bennu?
I think I talked about this a bit. So we picked Bennu because of its carbon-rich composition. And we also picked it because of its Earth-like orbit, right? So we had a lot of engineering constraints when we were originally designing the mission. We didn't want to overachieve. That is, we didn't want to get the spacecraft too close to the sun where it could get really hot. We didn't want a complicated thermal control system. For example, like the Parker Solar Probe, the amazing mission NASA has to touch the surface of the sun. It has to deal with those intense temperatures in the inner solar system. We didn't want OSIRIS-REx to have to overcome that challenge. So we couldn't have an asteroid that wandered too far into the inner solar system. We also wanted to use solar power. And we didn't want giant solar arrays because we had to do precision maneuvering around the asteroid. And the solar wind pushes you around just like a ship on the ocean. So we wanted to stay relatively close to the sun. So that gave us a narrow band of a little bit closer than the Earth and almost as far out as Mars, where we could look for asteroids. And then the final orbital criteria was the inclination. When that capsule enters the top of the atmosphere, there's a maximum speed at which it will survive. And if the asteroid is orbiting at a plane much higher than that of the Earth, it would exceed that capability, and we would lose the capsule as it passed through the atmosphere. So we needed what we called an inclination of less than 10 degrees. So those basic orbital constraints really narrowed down the population of asteroids that we could target. And then Bennu rose to the top of the list because of its size. It's pretty big, right? Like almost over 1,600 feet or 500 meters in diameter. And it's rotating relatively slowly. And most importantly, it had that dark surface, which we believe indicates a carbon-rich composition. And of course, we're going to verify that in the weeks and years ahead.
AstroXO on YouTube asks, how far away was Bennu from Earth when OSIRIS-REx collected the samples? Who wants to take that one?
I'll go. So because Bennu's on an Earth-like orbit, but not exactly on Earth's orbit, sometimes it's real close, as we talked about earlier, maybe a little too close in the future. And sometimes it's literally on the other side of the sun. And when we sampled, it was the latter case. It was over 2 astronomical units away, or what the way I like to think about it, in light time. It took over 18 minutes to send a signal from the Earth across the solar system to the spacecraft, and then over another 18 minutes to hear back. So we were looking at almost a 40-minute round-trip light time. And that's kind of how you measure distances when you're flying a spacecraft. How long does it take to send a signal? How long does it take to receive a signal? And because of that time delay, we had to have the spacecraft be really smart. It had to make its own decisions and guide itself down to the surface for that sample collection event.
Wow. Guys, these questions are great. Please keep sending them in. Again, remember, you can use the hashtag AskNASA on social media or anywhere where you're watching this show here. Okay, Marina Rapan on Facebook asks, what are the chances Bennu surprises us?
100%.
Well, both of you, same time said it. Who wants to go first and explain that?
Go ahead, Scott.
That was an easy question. Well, I mean, I fully expect that we'll find some things that are similar to what we anticipate, and we'll find some things where we sort of ask ourselves, you know, who asked for that? And that's, you know, part of the joy of doing this kind of analysis is the surprises make you sort of back up and realize that your image of what happened needs to be revised, and that's sort of how you advance your understanding. And so I will be surprised if we are not surprised by something.
That's right. Yeah, Bennu is the trickster asteroid. You know, it's been challenging us from the beginning, and I fully expect that's going to continue with that sample. And I can't wait now because the engineering tasks are done, right? Like Lockheed Martin delivered this sample beautifully to us on Sunday. And so all the surprises are science surprises, and that's why we got into this business in the first place. So, you know, as Scott said, right, we're expecting to be surprised, and that's the best part of your career is like when you're like, wait a minute, I didn't even think of that. And now it means these 10 things about the formation of the solar system that nobody had really thought about before.
Yep.
Scott, this might be the most difficult question you're going to get today, but what are you most excited about, looking forward to studying the sample? What are you most excited about?
Well, I'm sort of an organics guy. One of my other jobs is to run an astrochemistry lab at NASA Ames, where I try to simulate conditions in space to find out how radiation and ices can be converted into complex organics, particularly with an eye towards what role these organics can play for astrobiology, for seeding planets with both interesting molecules that can play a role in starting life, but also just delivering carbon, oxygen, nitrogen, hydrogen, the kinds of elements you need to make a biosphere, to make a planet habitable. And so I'm really interested in seeing the organics we get because they're going to tell us a lot about those kinds of things. I can compare them to my lab results and try to understand whether the chemistry we're simulating is right. And then someone that asked a question about how old the asteroid is. Components of the asteroid will actually be older than the solar system. We will almost certainly get interstellar grains that are remnants from other stars. and we'll probably get some material, including organics, that was formed in that giant molecular cloud phase that gathered up the material that ultimately collapsed to make our solar system. So I think the organics are going to be really interesting because they're going to come from before the solar system formed. Some were made while the solar system was forming, and some will have formed on the Bennu parent body while it evolved.
Wow, that's really exciting. Can't wait to see what you discover. Metanoia on X asks, what will happen to the samples after analysis is done? Will they go to a museum?
Great question. So, we're here at Johnson Space Center in the Astromaterials building, and I'm looking right out the window here is where the Apollo lunar samples are curated to this day. And they were collected from 1969 into the early 1970s. And researchers around the world can still request those lunar samples for analysis in their laboratories because the instruments are now much better. We have all the knowledge that was gained over 50 years of scientific investigation. So we keep pushing forward and learning new things about the formation of the moon and the formation of the Earth. And the Bennu samples are going to be the same. So they will be here at NASA's Johnson Space Center where they are protected, they're cared for. I dare say they are loved by the curation team that's here, with the job to take care of them. So they will be available for researchers for decades into the future. Some will go to our international partners. We're really proud to have the Canadian Space Agency as a partner on OSIRIS-REx. They contributed the amazing OSIRIS-REx laser altimeter. We have the Japanese Aerospace Exploration Agency, JAXA, part of our science team, as well as having exchanged asteroid samples from their Hayabusa 2 mission. So they will get material from Bennu to thank them for their contributions and to recognize the importance of international collaboration. And some of the material will be going into museums. We expect that there'll be one at the Smithsonian National Museum of Natural History in Washington, D.C. Probably in November, that display will open up. And we'll get some in Tucson, where the University of Arizona is based, where I'm a professor, at our Gem and Mineral Museum there. And possibly other museums around the world will be requesting and be able to put Bennu samples on display so everybody can come and enjoy the scientific treasure. So it's going for education, it's going for science, it's going to be a legacy that persists for decades and decades into the future.
Yeah, I love that we're able to share this with the world, with the public. Actually, since you mentioned the Japanese asteroid research, so one person on YouTube asks, what makes this sample return different from the Japanese return missions, and how different is this asteroid?
Yeah, so we have worked together with our partners in Japan really from the beginning of both of these missions. And the fact that both NASA and JAXA decided to fly one of these kinds of missions shows you the real value that they have. And the Hayabusa 2 mission went to asteroid Ryugu, which also appears to be carbonaceous. And we verified that with our sample analysis campaign that has been going on for the past few years. Their samples came back in December of 2020. They brought back about 5 grams of sample. We still don't know how much we have. That's one of the things we're really excited to find out is what is the mass inside that tag SAM, and we're going to take a little while to figure that out. But we believe we have about 50 times as much. And that opens up a whole new realm of scientific investigation because, as Scott mentioned, right, he studies ices and how they interact with radiation and new organic molecules may form, some which may be central to biology, like amino acids and nucleobases. You need a lot of material to really get down to the trace organic chemistry that we're interested in. And the large mass returned by OSIRIS-REx is going to open up that whole new area of investigation for us.
Wow. Scott, a viewer on X asks, does the sample contain water? If so, did it thaw on the way here?
Well, so we think that it probably contains water. The spectral data we got at the asteroid indicates that there are materials present that are kind of minerals that are kind of like clays where you have water content in them, and we certainly see a spectral feature we associate with the presence of that. So we fully anticipate we'll find some water in the samples, and one of the things we'll want to know is, what does that form? Is it water adsorbed to the minerals? Is it structural water where you have oxygen and hydrogen integrated in the mineral, and so on? But we are anticipating that we'll measure those kinds of things.
Let's stick with you, Scott. So Mark Jones on Facebook asks, do you expect to find live organisms in the sample?
No, not unless they get in as contaminants, and we're doing lots of work to make sure that doesn't happen. I mean, one of the things Dante and I were doing at the recovery was obtaining environmental samples of where we came down so that we know what potential contaminants would look like if any of them managed to get into the capsule. And so we'll use soil samples from this environment to make sure that nothing we measure is actually from Utah, it's all from Bennu. But we don't expect living organisms on Bennu. They wouldn't survive there. And our every effort has been to keep the sample inside as absolutely pristine as we can. So we do not anticipate finding any kind of living creatures inside at all.
Thank you for that answer. Jeff Meyer on YouTube asks, was there an anomaly with the parachute drogue chute? Dante, maybe you want to take this one.
Well, I can tell you that parachute did exactly what it needed to do. It opened up and brought that capsule to a gentle landing in the Utah desert. I know our colleagues at Lockheed Martin are going to reconstruct the entire entry, descent, and landing sequence and understand the details of how it all played out. I do know that we had a drogue chute which deployed, and we had a main chute which deployed, and the exact timing of that sequence is what the Lockheed team is going to reconstruct. But I can tell you there was no happier moment in my professional career than when I heard main chute open. And you can see this fantastic footage, by the way. This is from NASA's WB-57 aircraft that was flying at 50,000 feet above our sampling site, and they got that beautiful shot of the parachute open and gliding gently down to the surface. So I don't know the technical details. My job is not to design the parachute system. My job is to guide this mission to get a sample safely down to the Earth, and that was done to perfection.
Nicole is cool on Instagram asks, what type of Earth rock is Bennu most similar to? And related to that, we also have this question from Jazz Chavez on Facebook. What is the difference between the components of an asteroid and the rocks that we see on Earth?
Well, of course, we need to do the sample analysis to really know for sure. So all we're working with is what we learn from our cameras and spectrometers on the spacecraft. But I do have a student at the University of Arizona who's looking at rocks from the mid-ocean ridge that are called serpentinites. And they're characterized by a particular mineral called serpentine, which kind of has a wavy crystal form to it to give it that kind of cool name. And those rocks form when material from the mantle of the Earth, which makes up the bulk of the rocky material of our planet, meets the water from the ocean, and the water starts to react and make those clay minerals that Scott was talking about earlier, where you get water inside the crystal structure. We do see spectral evidence of serpentine on the surface of Bennu. We see other kind of salty minerals called carbonates, which viewers might be familiar with as the white crust that forms around your faucets. If you live in an area with hard water, that's calcium reacting with the carbonated fluid to make calcium carbonates. We see iron oxides, and we see the organic material. All of those also occur at these alkaline hydrothermal vents near the mid-ocean ridge, where mantle rocks are serpentinizing into those other rock types. So I think we might be looking at something like an oceanic hydrothermal system.
Serpentinizing. That's my word of the day. On YouTube, Scott, I think this question's for you. How was the sample return capsule landed so precisely in the Utah desert? The capsule itself didn't have any thrusters.
Yeah, so if I was surprised by anything when we got there, it was that it was sitting right on the nose cone there. That when the Stardust sample return capsule came back, it bounced and spun and rolled on its rim for a while and laid down and rolled around. And so I was expecting for there to be a more complex ground path. And to see it just sitting there right on the nose cone, it didn't even tip over onto the side, just really caught me by surprise. But you can kind of see in this image to the right, there's a bit of a shadow and a little lip of soil sticking up. And that's when I finally understood how it ended up on the nose. It must have come down with almost no crosswind, so it came down almost near vertical, hit right where it is now, and bounced up and tipped to the right in this image. And the rim there, the outer rim, gouged into the soil and plowed up that little thing that's sticking up, and that stopped it from skittering any further, and then it just rolled back into its original hole. And so this is a really strong indication.
Oh, sorry. Go ahead, Scott.
Go ahead. Yeah, go ahead.
I was going to say, to add to that, the question was also about the fact that it didn't have the thrusters, and that's a testament to the flight dynamics team. which is the group of engineers that plan the trajectory, and the perfect spacecraft, which launched the capsule on its 4-hour journey through near Earth space before it hit the top of the atmosphere. So, I like to use the analogy that the spacecraft was the quarterback and the flight dynamics team was the coach that told it where you needed to be and how far and how fast you needed to throw it so that it hit the exact spot at the top of the atmosphere that allowed it to fly over California, Nevada, and into Utah in 13 minutes to land down into that perfect position that Scott was just describing in the Utah desert.
Yeah, I don't know if you can pull that last picture up again. If you could pull up that last picture that was on. Yeah, so the round dark area you see on the left is where the nose was sitting in there, and the mark to the right of that is where it tipped over on its side and rolled back. And all that black material you see there is char that the damp soil of the Utah desert sucked off of the heat shield. So that's material that basically soot that was still on the very surface of the capsule, and the clay sucked it off. And that actually was a benefit to us, because that soot, when it got sucked off, formed a layer between us and the Utah soil. So very little Utah soil adhered to the SRC, so we didn't have to worry about that as a contaminant that was carried off with the capsule.
Wow. Jordan Chapa on YouTube asks, what inspired the creation of the OSIRIS-REx mission?
Well, I think it's human curiosity, right? So 20 years ago, I was a young assistant professor, and I was driven to try to understand the origin of life and the origin of the Earth as a habitable planet. And I came to realize we can only take our meteorite research so far. And if we get into the exact compounds that are used in biology today, like the 20 amino acids that are critical for our proteins and the nucleic acids that make up our genetic material, those are contaminated very quickly in meteorites by bacteria. They probably are munching on the same compounds their ancestors did, 3.5 billion years ago, not too long after the origin of life on Earth. So we lose that information when it comes in as a meteorite. And I started to realize, boy, if you really want to try to go after this question rigorously scientifically, you got to get out to one of these carbon-rich asteroids and bring it back in a pristine state. I'll admit it seemed like magic at the time that I was thinking about it, but 20 years later, here we are with the samples in our laboratory, and we're about to address some of those critical questions.
Yeah, you can learn a lot from meteorites, but they're all orphans, so we don't know where any specific meteorite comes from. And so one of the things this mission has done for us is, the SRC said, here's a sample, and you know where it came from. So you can tie this to home base, and that's going to be a huge benefit for the rest of the analysis.
Yeah, that's important to know, because actually a lot of people were asking that question. I was about to ask you this question, actually. What is the difference between studying a meteorite that falls onto Earth versus going out there? So thank you for clarifying that for our viewers. Another question is, how many divisions of science will get to study the sample?
That's an interesting question. So I know we have over 200 scientists using about 60 different analytical techniques. And the OSIRIS-REx science investigation really is astrophysics, astrochemistry, astrobiology, planetary formation, stellar evolution. Scott alluded to those interstellar grains, which formed in nucleosynthetic environments in ancient stars. And probably things we haven't thought of before, right? Because they're available to the world, these materials, and there's people asking questions that this science team hasn't addressed yet. So if it involves outer space, then you'll be able to work with the Bennu samples to come up with some answers to your questions.
And part of the power of having the sample back is that, 20 years from now, if someone has a new technique, they can take the sample out and measure it all over again with a new technique. So these things will just keep giving. And so, with this question of how many fields are involved, well, maybe there'll be new fields in 10 years that we don't have a name for yet, and they'll get to measure it too. So.
That's a really great point. Donnie Mertz on Facebook asks, how can you tell how old Bennu is?
So we have, inside these rocks, there are little clocks. And when I say that, what I mean is there's elements that are radioactive, and they decay with a very predictable half-life. So one of the ones that we'll be looking at that's most important is uranium. Very well-known chemical element because it's used in nuclear energy and nuclear reactions. And it turns into lead. So we're going to look at the abundance of uranium. We're going to look at the abundance of lead. We know how long it takes uranium to convert into lead, and we can use the abundances of those elements, and in particular specific isotopes, which are different forms of the same element that have different atomic masses. And we can then calculate how long that system was undergoing decay without any disturbance, without losing lead or adding uranium or anything like that. And there's other similar systems that we use. They all generally involve radioactive elements that decay in a very predictable way into elements that we're familiar with. And we can look at the abundance of those two and then determine how long that process took to go to reach the state that we measure.
And there may be some small amounts of material like these interstellar dusts I mentioned earlier where we won't necessarily be able to date it, but we'll know that since it comes from a star, it predates the solar system, so we can put a minimum age on it. And we'll undoubtedly find some of that material too.
David Colburn on Facebook asks, did we discover that the surface of Bennu was not as dense as previously thought?
Yeah, I mentioned earlier that Bennu's the trickster asteroid, and that was one of the final tricks. When we went in to collect the sample, Scott talked about it earlier. We had these great computer animations of what we thought was going to happen as we were going to hit a solid surface, basically, and grab the material right off the top. But when you look at this amazing footage, you can see that we really moved a lot of material there. I like to use the analogy of one of those ball pits at a kid's playground, right? We just sunk right into that asteroid surface with almost no resistance whatsoever. And we went in, about a foot and a half, like the length of my arm, down into the subsurface of the asteroid, where we predicted we might go down an inch or so at the most. So it was very soft. And as we analyzed the data, we realized that's because the density was incredibly low. It's about 1/6 the bulk density of your average rock on Earth, and about 1/2 the density of water ice, which is one of the lowest density major solid materials that we know of in the solar system. So Bennu really surprised us in a good way in this case, because we went so deep and we were in contact with the asteroid for a lot longer than we expected. We got a lot more material than we had designed the mission to.
Gosh, this mission has been so exciting for the last 7 years. All these questions are talking about launch, we're talking about collecting the sample, and now here it is back on Earth. So really thrilling. We have another question on YouTube. Naeem Ahmed asks, what are some of the most innovative and exciting experiments that scientists could perform on the asteroid sample?
Scott?
Well, I almost hesitate to suggest anything because I don't want to diss anybody else. Dante mentioned how many analytical techniques we're going to apply to these samples, and they're frankly quite amazing. I mean, there are people basically counting atoms of different elements or even isotopes, tearing these rocks apart down at the atomic scale, and there'll be people worried about these rocks at the molecular scale, and there'll be people who are worried about these rocks at the mineralogical scale. For minerals, and the petrologists will want to know which minerals are next to other minerals, because that tells you something about the environment and puts constraints on what has happened. And they're all amazing in their own right. I mean, they all provide information which is really unique. That's why we're using them all. And so I'd be hard pressed to say one's better than any of the others. What'll really be powerful is the use of all of them in combination, because then you can see, every technique will see some things that make sense and some things that puzzle them, and the things that puzzle them may be addressable by information that comes from another technique. And so sharing our data, putting it all together is going to allow us to figure some things out that no individual technique would sort out.
It's that collaboration that's great. You guys have been talking about it throughout this entire show.
Yeah, so the team is going to continue being a team.
I love it. Another question on X. Could there be a world where the sample contains any elements not known on our periodic table?
Well, we have the periodic table pretty well figured out at this point, so I don't think we'll discover any new elements. But what we may find are new minerals, which are combinations of elements that occur under environmental conditions that may not happen on the surface or in the interior of the Earth. So the chemical elements are very well understood, but the minerals, you can always find new minerals because these are very different, literally alien environments compared to what we have here on Earth. And we do find a lot of unique minerals in meteorites that don't occur in terrestrial environments. And I wouldn't be surprised if we pull something out of Bennu that we haven't seen before in that regard. It's how how the atoms are arranged in crystal structures to make a mineral.
Well, you have said Bennu is the trickster asteroid, so I'm pretty sure you'll be right. This is another question on X. Is there something, and Scott, it sounds like this one's for you, is there something or what is in place to guarantee that entry into Earth's atmosphere did not affect the samples?
Well, so we live on an Earth full of biology and organics, and so there are no guarantees, and so the approach we've taken is to do everything to keep it as clean as possible, and also do everything we can to make sure that we can recognize anything that doesn't belong. So, for example, in these environmental samples, if it, for some reason, although given the way we landed, I doubt it, it's highly unlikely, but if a little piece of Utah dust got through the back vent and got into the SRC, since we have these environmental samples, anyone who sees that says like, wow, this is different from all the rest of this. Maybe Bennu had a salt lake on it. Like Utah, we'd say, no, look, compared to the soil, you'll find out you've got a little piece of Utah there, set it aside. And so you do everything you can to prevent contamination, and then you also do everything you can to recognize it if it happens. And in the case of organics, since we are in an environment, we're just surrounded by organics, you need to work very hard at that and be very careful and make sure when we measure things in the samples, we're going to be spending a lot of time trying to convince ourselves that this is really from the sample and not from any place else.
Right. This is a fun question, actually. Matt Pike on YouTube asks, how do you think your peers from the early Apollo missions era would react to the fact that we are now able to return samples from asteroids?
I would think they'd be really proud because it's their legacy, right? And their vision and their inspiration. A lot of us were inspired by those missions to go into these kinds of field and to ask these questions and to realize you can do something amazing like this, right? When you have the right team and the right support and the right environment. And they were the ones that showed it was possible, right? They were the pioneers. And so we owe a lot to the legacy that they left behind. And when you're here at Johnson Space Center, you can't help but feel it because it's around every corner, right? You see some historical memory from those eras, including those great rocks, which are right across the way here in Building 31. And that legacy has inspired, I would think, all of us in this business.
Emmy on YouTube asks, how heavy is the sample?
Well, that is to be determined, right? We were able to make an estimate while we were in outer space, but that's hard to do. And we actually didn't get to use the sample mass measurement technique we designed because we had that challenge of collecting too much sample, and our collector was overflowing. I use the metaphor of a bucket that you fill all the way to the top with water, and then if you try to move it around, you're gonna have to lose some of it over the lip, just it's a little bit unstable. We estimate there's about 8.8 ounces or 250 grams in there, but that's what we're going to be doing over the next couple of weeks, is getting all of that material out of that tag SAM, getting it into containers that we know the weight of very precisely, and then figuring out how much the sample weighs now that it's here on Earth. So stay tuned. I think Megan talked about the October 11th event, and that is something that we should have for you by then.
Yeah, I'm getting a lot of the same question, really, and I know we touched on it before, but why don't we revisit it since we're getting a couple of the same questions. Again, how long before we know what is in the samples?
So we're hoping, because we opened up the canister today and we did see that there is some black dust-like material that's visible. We're hoping that's from Bennu. So we expect that we'll be collecting a portion of that in the morning, tomorrow morning, and that'll go right into the laboratories. We have a team that's standing by. We have instruments that are at the ready, and we'll be getting data tomorrow. And by Friday, we should have a pretty good sense of what that quick look analysis is telling us. First of all, do we in fact have asteroid dust? That's the first thing. Is it the kind of material that we expected based on the remote sensing that we did at the asteroid? And how does that feed into our sample analysis plan, which we've been writing over the past 2 years in great detail? Can we follow the plan, or is Bennu tricked us so much we need to kind of rewrite that plan? from scratch, right? And I'm hoping that's not the case because we put a lot of work into that. And then that's the quick sample. So that's just the dust that we can visibly see right now. The real treasures inside TAGSAM, which we're not going to get access to until probably late next week. And then it's going to be a very deliberative process to figure out what is the nature of that collection and how do we fairly distribute it to our international partners, to the science team for OSIRIS-REx, and also preserve the long-term integrity for future researchers. So we got to stay tuned. I know it's hard. You got to be patient. But trust me, nobody is working harder than I am to maintain our cool while this team carefully goes through their process to get that material properly curated and safely to the science team.
I like the distinction you made, that quick look, the first kind of analysis is basically the sample that you're seeing outside of the collector before, you can say some of those bigger discoveries, really you got to get in there, but that's going to probably be at the end of next week, like you said. Okay, so we're actually running out of time. I hope that we got to as many questions as we could have. I know that we were getting a lot of questions, so thank you to those who've sent in the questions, as well as also you guys for answering those questions. But I do have one final one. We're talking about this being the first U.S. mission to bring back an asteroid sample to Earth. Again, let's just hammer home for everyone why this is so significant. Is it, yes, the scientific discoveries, but also the legacy that this is going to leave?
Yeah, I'm really proud of the OSIRIS-REx legacy already. We've done a phenomenal job characterizing asteroid Bennu at a higher resolution than any other planetary body in the solar system. So that already is unprecedented. And of course, we brought that sample back down to Earth, and it's going to be here at NASA's Johnson Space Center for decades into the future. Sample return is the gift that just keeps on giving. We're going to have a great science analysis program over the next 2 years, but there's going to be people in the future that are going to be smarter with better instruments and building on the knowledge that we've accumulated. So I expect for the rest of my life, I will be reading papers about the analysis of samples from Bennu and being surprised and learning new things by all the clever people in the future that are going to ask those great questions and get those amazing answers.
Yeah, I'm sure this will inspire, upcoming generations to really get into this field and figure out, all these questions we still have about our solar system. So it's really wonderful. Well, thank you, Dante and Scott. It was so great chatting with you and learning about NASA's OSIRIS-REx mission and all that is planned to come.
Thank you, and thanks to all of the viewers and those fantastic questions. It's really great to hear from you. Keep asking us, right? We can still get Ask NASA questions, and maybe we'll be able to answer them on social media in the future. So please stay engaged. We love you guys. We appreciate your interest, and thank you for a great NASA Live.
I second all of that.
Scott, a man of few words. When Dante says it right,
But thanks for having us. I mean, it's been fun.
Oh, yeah, it has been fun and very engaging. Like Dante said, it was really great to see all the questions that were coming in. I tried to get in as most in as possible, but there was a lot to cover. So again, thank you to everyone who joined us online. And I love that we were able to answer so many questions. We hope you keep following NASA's efforts to study our solar system and beyond. And you can do that by following NASA Solar System on Facebook, X, and Instagram. To stay updated on this mission, you can visit nasa.gov/OSIRIS-REx. There will be a lot of exciting findings from this asteroid sample, as you heard both Dante and Scott tell you about, and we want you to be a part of this journey with us. Finally, remember, this is just the beginning of what we will learn from this asteroid Bennu sample. Tune in again October 11th at 11 a.m. Eastern Time to join us as Dante and his team reveal what they've learned so far from the sample of Bennu. Thank you, and we'll see you next time.